title is Romanian Syllabification using deep neural networks. So in this case, the paper proposes a model for syllabification of the Romanian language based on deep neural networks. So please, Dragos, the floor is yours.
Hello, everyone. My name is Dragos-Corlatescu, and today I'm going to present the work of Stefan, Mihai, and myself called the Romanian Syllabification using deep neural networks. What is syllabification? Well, the syllabification, as you probably know, is the process of splitting a word into syllables that are generally marked by a hyphen. The division points are generally language specific and can be done by humans pretty easily, let's say, but there are some cases where the correct syllabification is not that obvious, maybe because, let's say, they sound good in both ways, as I said here, for example, for Romanian geography, geografie, how is it spelled correctly? How is syllabified correctly? With this, as you can see here, the J-O is split differently, or is it together? Also, there are some problems when talking about general systems, when the part of speech can be different. For example, here, the word haina or haina, it has the same writing but different pronunciation, and thus the syllabification is different. So those are the challenges that may make this problem not that easy. Where can we use the syllabification? Where this is the basic block for every language, especially for Romanian, and we can use this syllabification when talking about conversational agents that can speak to you, text-to-speech maybe in a smart learning environment, smart home, and so on. And also for systems like a platform that can teach children to maybe speak, maybe syllabify some words. So there are many places where a syllabification can be used. How can we solve this problem? Is this solvable? Well, yes, I would say, but there are mainly three approaches to this. You can hire, let's say, language experts that can enumerate all the possible word syllabifications, but this is time expensive and so a lot of work to be done. We can also use the rules to enforce a certain way of syllabifying the words, but there aren't that good, maybe more sufficient. Maybe for some languages that can be done, but for Romanian, there aren't rules that generally cover all the cases. There are, let's say, maybe 6 DOM, which is a dictionary rules that can be applied, but they are not general and cannot solve everything. And the third one is the statistical approach. And that is what we are doing here for the Romanian language. Related work. So there are multiple research studies that were built on this domain depending on the needs. So the first one for this kind of work was actually the hyphenation part of the typewriting system to make sure that you hyphenate correctly, and there are some limitations in terms of memory. And then coming closer to now to current date, there are multiple researchers for specific languages, and one to mention is for English, of course, which the best result was obtained by Bartlett, Konrak, and Cherry that used a support vector machine alongside with a hidden Markov model. And they were the first one to introduce an interesting idea, the onset nucleus coda, which means that the vowel will be the nucleus of a syllable, and then the parts that are in front is the onset, and the parts that are behind is the coda. And the goal of the model is to determine which letter it's which given those three classes. For Romanian, There are multiple studies. We just mentioned 3 that are more relevant to us, but there are more. The first one is a model that uses the support vector machine alongside with a conditional random field by Dio, Nicolai, and Sura, which obtained the 95.25% accuracy on a word accuracy. So you have to syllabify correct the whole word, not just some syllables. The other 2 are kind of made the state of the art. The Mira system that made by Boros, which also uses the Onsen nucleus code idea, which obtained the 99.01%. And the state of the art at the moment is an ID3 model implemented by Boros, Dumitrescu, and Pipa, which had a word accuracy of 99.70%. Our corpora, we started with a corpora of Barbus corpora, which is a raw syllabification dictionary, but it had multiple mistakes that we actually tried to fix. But after multiple manual appliance of rules and using DEX, we decided that it's too hard, multiple mistakes that can affect our models. So we switched to another dictionary, another corpus, which is the Romanian Academy Explanatory Dictionary that had approximately 600,000 manually verified words. Those words were grouped by lemma, and they also provide, besides the syllabification, obviously, the part of speech. And starting from this, we decided to split, kind of a standard way to do things. We split the corpus in 3 parts: train, development, and test. Train 60% and the other 20%. And we used 2 methods to split them. The first one is a lemma split. So basically 2 words that have the same lemma will be placed in the same split, in one of the three here. The idea behind this is that even though maybe the words with the same lemma doesn't have the exact same syllabification, they may have some similarities. So we don't want to overfit, to see those examples and then maybe make some specific adaptation to those words or to those form of the words. And the second method was to just basically a random split that didn't take into consideration the lemma. So just random. So in theory, the lemma split will be harder and will be more relevant to the whole experiment. In terms of architecture, what do we use? Our first approach was to use the sequence to sequence. So you have a text, and you give back another text with the hyphens in the correct place. But that was a little bit too hard because the model also had to learn to give back the actual letter. And we switched to a sequence to binary model where a model has to go to give back 0 or 1. That means 0, leave the letter as it is. 1, put a hyphen after the letter. We used, because this is a sequence problem, we used 3 of the most performing layers architectures. In here, the BLSTM, the bidirectional long term memory, the convolutional neural network, and a transformer. We put these layers into this architecture where we use the characters of the word that we then learn an embedding for them. Then we make another layer. Then we apply this so for the BLSTM or CNN or transformer here. Then we apply a dense layer. Now there were multiple iterations in here where we only used the embedding layer or the characters, which perform okay. But then there are some problems for the first examples with Heine and Hyena that depend on POS. The syllabification are different. So we also added the part of speech as input, and then we concatenate here. And lastly, another adjustment that we made, we also added a conditional random field layer on top. So there were multiple iterations. This architecture here is the one that obtained the best results. Okay, so talking about results. So in here, as I said, we have multiple iterations. The first one is just having only the characters used without the part of speech, and the dense layer was one who gives the 0 or 1 result. You can see here that BLSTM is performing better. Then we tried to again use the pause, the part of speech of the word. In here there were two possibilities. So one was to basically compute everything and then try to decide on the last layer using the part of speech where to put the hyphen or where to give 1 or 0, or to use the part of speech alongside, combine with the characters and try to start it from there. The difference between the two approaches in here, we're using part of speech, were not that different. You can see here. Maybe the one that you use part of speech at the beginning, as we can see here, did a little bit more, but 0 point something better results. So we decided to go with those approaches, and then again, the BLSTM model performed better. And our last iteration was to add a conditional random field layer on top of that, but just for the one that performed better. And you can see here the results, which is indeed actually better than anything else in here. The last row is the comparison with the previous state of the art that I mentioned, the IDE model. We couldn't test on the same corpus that they used because they reported the dataset that we couldn't find online. So we applied this. The model is freely available online, and we applied the model on our dataset. So you can see here that it works better. Our model works better. On the other hand, so note that this was tested on a lemma corpus, right? When I said the lemma tool works with the same lemma, we're in the same split. When we did the same thing on just a random split corpus, we can observe that we have a better accuracy overall, which I know what the dev 99.87, 99.60 on a test environment. So then still performing better than the last previous state-of-the-art model.
Couple of minutes.
Sure. Conclusions and future work, where we explored all the different ideas, different neural architectures that took into consideration the top of the state-of-the-art models that can be applied to a sequence problem. For the Romanian Syllabification task, the results are the best so far, and with the best model being the one that took into consideration the word syllabification, obviously, but alongside with the part of speech of the word, using a BLSTM model, and the output model was actually a conditional random field layer. In terms of future work, we want to integrate our model to related tasks, such as in NLP, determine the rhythm of the text. The syllabification can help in this. Measure the complexity of the words, and speech-to-text synthesizes. And as I said at the beginning, we want to build, or maybe to help to build a conversational agent where it requires to speak, and that can help the syllabification part. A platform maybe for children to learn, to speak or to syllabify words, especially for Romanian. And lastly, to maybe extend our model, our ideas to some other languages, not just the Romanian language. Thank you, and if you have any questions.
Thank you very much. Can I ask you, I'm interested in the more in the pedagogical perspective. So at the beginning, you mentioned some possible uses, but can you elaborate a little bit more in terms of implication of using your models? For smart learning ecosystem. So, for example, now you have mentioned the fact that you are planning to develop a platform for children. So how do you imagine it? Can you tell us something more in terms of pedagogical perspective?
Sure, but these are just some ideas. We can do this mostly thinking about word games, where you have some words and you try to play a game where you try to syllabify correctly, especially in this, let's say, corner cases that are not too obvious. This platform, I think, will involve some kind of gamification. I mean, some rewards, some achievements. So this is just trying to learn to syllabify. Also, maybe we can extend this to speech, right? So try to make something to children to speak.
Are you thinking at this for children speaking Romanian as a native language, right? Not at I mean, or are you thinking at I mean, language learning? One language is your second language.
No.
Is there any difference? I mean, or
the main idea is for the first language. So you have a children that is learning. Sorry, it's native language is Romanian. Mm-hmm. Maybe we can extend to some other for other languages also. But I don't know, practical. I don't know how many people are learning this kind of stuff. I try to learn new language. How hard is it, or how much do you want to learn to spell or to syllabify correctly? Maybe it can be used, but for now the focus will be on the children that are speaking Romanian.
Okay.